Welcome back to this YouTube tutorial series on implementing templates/generics in C. And in today's video we're going to be actually implementing a fully functional stack data structure as a template. So to begin with, what exactly is a stack? A stack is known as a LIFO data structure, aka last in first out. It has two main functions, the push and the pop. We're able to push values onto the stack and be able to pop them off, where the pop statement can only return the top of the stack. So any value stuck at the bottom will have to wait until there's no value at the top. And so this data structure is very useful. And so to begin with, instead of actually implementing our stack data structure inside our main.c file, I'm going to create a header file and another another .c file for it. This allows us to include these two files in other projects besides this one, and this just keeps with the notion of making our code reusable. So to begin with, we're going to go to our stack.h file, and we're going to have a few quick statements. So we're going to say if not define stack.h, define stack.h, and if stack.h. So what exactly does this code mean? Well, in our main.c, whenever we include our stack file, the compiler actually takes the code in this file, and translates it into object code inside of our main compiled sequence. And the problem with this is if we have multiple files and each of these files uses the stack.h, we could become our object code would become very long. We would have multiple sections of our object code just of the same chunk of code, namely stack.h. So to get around this, we have an if not define. So we're going to say if the stack.h does not exist, which means if not define, then we define stack.h. This way, the first time we have an include statement, it's going to it's going to define a stack.h. So then the next time we have an include statement and it reaches that include statement, it's going to go to this file and it's going to say, oh, do we have stack.h defined? Yes, we do. Continue. So then that way we don't have multiple reoccurrences of the same data. So in a stack, we have some common functions, namely pop, push. We can even define a get size. We can define a destructor for it. We can define an initializer, and we can define a contains. Excuse me. We can also define a free nodes, and we can define. Excuse me, not free nodes. And we can define a contains method. Now the contains method is not necessary. However, for this purpose, I actually want to define a comparator function. So in the last video, when we went over the qsort function, we actually made our own comparator function. But in this video, I want to actually make our own unique comparator function for different types of data. So to begin with, we are going to make our structure inside our header file. So first off, a stack can be implemented as a linked list. So we're going to make a simple and short linked list. We're going to call its nodes stack node. We're going to have our void value. This way it's a template. And then what we're going to do is we're going to say struct stack node previous. And we want the previous value because, as we can see here in our diagram, if we were to have another value here, if we were to pop it off, we would have to go to the previous value and then the previous one. So there is no next in our linked list, but only a previous. So then what we're going to do is we're going to define using a type def. We'll say type def struct stack node. And instead of simply writing struct stack node over and over again, we can make a type def for it. So this allows us to actually make an alias for it. So we're going to say type def struct node is going to be referenced by here on out as stack node. And this is a very useful tool. So we're going to say struct stack. This is going to be our main data structure. And we're going to record the top of the stack as a stack node. So we're going to say top. Oops, not that. We're going to have a size, and then we're going to have two pointer functions, a compare and a free value. Before I get on to those, what we're going to do is we're going to have our stack node, as we can see here. And our stack nodes are simply just going to have our value, and it's going to have a pointer to the previous value. And we're going to make a struct called stack, and what it's going to do is it's going to have a pointer to the top value and a size. And so we're simply going to iterate through this top value whenever we're popping and pushing. And for a free value, we're going to say void because we're not going to return anything from this function. And you denote a pointer function inside a struct using the pointer ampersand. So we're going to say free value. It's going to take a parameter void star. So we're going to say this is a user-defined function for freeing values. And then our comparator function is going to return an int. So we're going to say compare. And just like before, it's going to be a const void star, const void star. We're going to say return we're going to return -1 if L is less than R, where L denotes left and R denotes R denotes right. 1 if L is greater than R, and 0 if L equals R. So now what we're going to do is we're going to implement the push, the pop, get size, destructor, and initializer. Now, if we include these data structures, and one more thing, we're going to say type def struct stack as stack. This way we can reference the struct stack as stack from here on out. If we include these data structures, these structs inside our stack.h file, we can actually grab them inside of our main. For example, if we were to say, we can now say stack my stack. And then we can say my stack dot size is equal to 5. However, the whole point of using templates is to make our code reusable. And another main, procedure or thinking is object-oriented programming. Now, C is not object-oriented, but we can sort of make it object-oriented in the following fashion. We can actually hide these structures inside of our stack.c file. Oops. This way, in our main.c, we cannot access these, except the only thing we can do is define. So we can define this as the following. Now I know we're getting an error right here, but however, we can leave this error here in a second. So we can define our stack as such. I'm going to include stack.h in our C file. And then now if we want to actually access an element of our stack, we have to use specially defined functions. And these functions are going to be pop, push, get size, destructor, and initialize. And so I'm just going to write these out real quick. So we're going to say void void star for popping a value. So we're going to actually return the value from this node, and we're going to return that as our pop. If we want to push a value, we're going to say stack.push, and what we're going to do is we're going to pass our stack pointer. And so now what we do, inside our main function, if we want to push a value, we're going to say stack.push my stack, and we're going to say, let's say null for right now. You can make this a pointer. So what we're able to do is pass a pointer onto our stack.push file. And now, even though we can't access the elements, the specific elements of the structure, once we get into our C file, we're actually able to access these elements. So it's a nice little trick of being able to hide things away from the user, thus making it almost object-oriented in nature. That way we can have private functions, private things, private variables and such. And so now when we go back to our other functions, we're going to have a get size, stack.get size. We're going to pass our stack variable. And then what we're going to do is we're going to have our destructor, so void that stack destructor. And now we're going to take a double pointer for this. And the reason why I say double pointer is because, if you remember correctly, in C we pass values by, we pass variables by value, not by reference. And so if we want to access the actual memory of a variable, we have to pass it by a pointer. So the only way for us to access, the only way for us to initialize memory of a pointer through a function, we have to pass a double pointer. And so, as you know, we can't actually assign this as a stack pointer by allocating memory. And the reason why is because we don't know the size of stack. It's because we've hidden the actual size from stack.h and we've stored it inside our stack.c. So if we want to make an actual pointer using allocated memory, we have to pass it as we have to pass the address of this pointer into our stack.c file and then initialize the memory there. And so now I'm just going to write these out. So we have our destructor, and then now we're going to have our void stack.initialize. So we're going to take our stack double pointer, and then also we need to pass in our comparator function and our free value function. And so we're going to take these, and I'm going to copy paste these into our initializer. So we're going to say copy and copy. So our initializer is going to take our stack, it's going to call malloc and initialize the memory necessary for the stack pointer, and then it's also going to take two pointer functions, and we're going to assign these to our stack. And this allows our user to define a custom compare and a custom free value function, where the free value is going to free the stack node values. And so because we're making a template for our stack, the void pointer star can take up any value. And so this could be a simple double pointer or a char pointer, or it could be something elaborate such as a struct pointer, which contains its own dynamic memory. So instead of just freeing the stack pointer and just assuming that it's just a simple value, a primitive type, we make it a free value type that's user defined. This way the user has the control and ability to accurately free the value. And that's all for today, and in the next video we're actually going to be implementing these 5 functions in our stack.c. So stay tuned.